So the last speaker of this session is Felix Hommelsheim. The next speaker is Felix Hommelsheim, and he will speak about flexible graph connectivity. Please.
Yeah, thank you very much. This is a joint work with David Adjashvili from the ETH Zurich and Moritz Mühlenthaler from Grenoble. And the topic of the talk will be flexible graph connectivity. That's a problem that we've introduced. And it's a network design problem between 1 and 2 connectivity, which means that some of the edges of the graph are more reliable than the others. And we would like to find approximation algorithms for this problem. Okay, first, I will talk about the motivation and the setting of this problem. Then I will introduce 3 basic algorithms for this problem, FGC, which are each on its own are not so good. Then we will see that actually scaling the cost of the safe edges, that is scaling the cost of the more reliable edges, so making them cheaper, is actually a good thing to do. Then we can state the overall algorithm, and finally we will talk about the approximation guarantee. Okay, first the setting. A very famous problem is a network design is the 2-edge connected spanning subgraph problem. Here we are given a graph and weights or cost on the edges. And the task is to compute a minimum weight subset of the edges such that we have a 2-edge connected spanning subgraph. So for example, an optimal solution to this graph here, to this instance, is this graph here. It's a cycle, and you can see, okay, it's a spanning subgraph, and also it's 2-edge connected. So which means that no matter which single edge you delete, like this one here, you still have at least a spanning tree remaining. Okay, the formal definition of this problem is, again, we are given a graph and the edge weights, and we would like to find the minimum cost edge set of edges x, such that the graph v, x is 2-edge connected. Alternatively, you can also define the problem as follows. The task, you want to find a minimum cost edge set x such that v, x minus f contains a spanning tree for all edges f and e. So, which means no matter which single edge you delete from your graph, you still have a connected spanning. You have a spanning tree. And the problem that we consider generalizes this alternative formulation, and we say that we don't have to fulfill this for all the edges, but only for a subset of the edges. So an example, so the problem we consider is, we call it flexible graph connectivity. Here we also have given a graph and edge weights. And additionally, we partition the edge set into safe and unsafe edges. And throughout the talk, we always have that the black edges, they are the safe edges, and the red edges here, they are the unsafe edges. And now the task is to compute a minimum weight subset of the edges, such that we still have a connected spanning subgraph, no matter which unsafe edge is deleted. So an optimal solution to this instance would look like this. Here you can see no matter which red edge, so no matter which unsafe edge you delete, for example, this one here, you still have a connected spanning subgraph. You can have cut edges like this edge here, but then it has to be a safe edge. Okay, again, the formal definition of this problem, we abbreviate it with FGC. We're given a graph, some edge weights, and each edge is either an unsafe edge, then it's an F, or a safe edge, then it's an F bar. And we would like to find a minimum cost edge set of edges x, such that v, x minus f is connected for each f in f. So here you see the difference. We don't have to fulfill this condition for all edges, but only for the unsafe edges in f. Okay, so the whole talk will be about this problem. Are there any questions concerning this definition?
No questions on the chat. So.
Okay, great. So as we've seen, this problem generalizes, for example, the 2-edge connected spanning subgraph problem. And it also has lots of other problems as special cases. For example, the minimum spanning tree problem. Simply, if all the edges are safe edges, then we have to compute a minimum spanning tree. The other special case, as we have seen, is a two-edge connected spanning subgraph problem. Simply, if all the edges are unsafe edges, then we have to compute a minimum two-edge connected spanning subgraph. And the third problem that I would like to mention here, which is actually a special case of the two-edge connected spanning subgraph problem, is the tree augmentation problem. And here's a definition of this problem. The tree augmentation problem, we are given a spanning tree and additionally some links and costs for these links. And now the task is to find the minimum cost subset of links, X, such that the tree plus this edge set X is two-edge connected. And well, since this is a special case of the two-edge connected spanning subgraph problem, it's also a special case of our problem flexible graph connectivity. And at first, I would like to mention some observations. So on the negative side, we know that the two-edge connected spanning subgraph problem is APX hard. And therefore, also our problem flexible graph connectivity is also APX hard, since it's the two-edge connected spanning subgraph problem is a special case. On the positive side, we know that there is a very nice two approximation algorithm by Jane for the two-edge connected spanning subgraph problem, and therefore this algorithm is also a two approximation for the tree augmentation problem. But a very nice recent result is that the tree augmentation actually admits a 1.5 approximation algorithm for bounded weight instances. And a bounded weight instance is an instance where here all the weights are in the range from 1 to some constant big M. So what we wanted to find approximation algorithms for our problem. And since the two-edge connected spanning subgraph problem is the special case of our problem, it would be very ambitious to improve on that two approximation. So we tried to find an approximation algorithm which had an approximation guarantee very close to 2. And here I state our main result. So our main result is a 2.5 to 3 approximation algorithm for FGC. And similar to this bounded weight instances case, we have a 2.404 approximation algorithm for bounded weight instances. Okay, and how do we obtain these results? So here's an overview of our techniques. We will first introduce 3 very simple algorithms, and they each have a worse approximation guarantee than our approximation guarantee in theorem 1. Then we will see that actually scaling the cost of the safe edges, that means we make the safe edges cheaper, so there is incentive to buy more safe edges. This is actually a good thing. And then we obtain a various number of new instances, and we then apply the algorithms B and C to these new instances. And then the approximation factor of our algorithm is an upper bound on the approximation factor is an optimal solution to this min-max-min problem. So if we can solve this min-max-min problem, then we have an upper bound on the approximation guarantee of our algorithm. And just to mention some of the variables here, FA simply means it's FA is an upper bound on the approximation guarantee of algorithm A. FB and FC are also an upper bound on the approximation algorithm for B and C, where here we have the index I for the different scaling factors. Then the maximum is over some values beta and gamma. And these parameters, they depend on the structure of an optimal solution. And since we do not know how this looks like, we need to maximize over these values. But we do know that they have this constraint. They sum up to at most 1. And finally, as we will later see, that actually in the analysis, we are free to choose the scaling factors that we use here in our algorithm. Okay, so we first going to introduce the 3 algorithms A, B, and C. And algorithm A is the easiest one. We simply compute the 2-edge connected spanning subgraph using the 2-approximation algorithm by Jane. And one can actually show that this algorithm is a 4-approximation algorithm. Algorithm B is a bit more involved. Here we first compute a minimum spanning tree, T1. Then we contract the safe edges of T1 to obtain a new graph and a new tree, or you contracted these safe edges of the tree. And then we have a tree augmentation instance, and we solve this instance using an approximation algorithm, either the 2-approximation or the 1.5 approximation for bounded weights. And then we output the tree together with a solution for the tree augmentation problem. And one can show that this actually is a 3-approximation algorithm. And since this algorithm is a bit more complicated, I will illustrate this with an example. So consider, for example, this graph. And for now, we neglect the weights. Then we first compute a minimum spanning tree, which might look like this. Then we contract the safe edges and compute the tree augmentation problem on this instance. So here we're given this tree here for the tree augmentation problem, and the remaining edges of this graph we add to this here. And now these dotted edges, they are the links in the tree augmentation problem. And then we compute a 2-approximate solution to this tree augmentation problem. And for example, it would look like this here. And then we transform it back to the original instance, and then it might look like this. And here you can see, okay, some edges might be cut edges, but since we only contracted safe edges, the only cut edges that might appear in the solution are safe edges. So we know that the solution that we've computed in this way is always feasible. Okay, algorithm C is very similar to algorithm B. Here we also compute a minimum spanning tree T1. Then we let T1S be the safe edges of T1. And now the difference is, compared to algorithm B, we contract the safe edges of the safe edges T1S, but we do not keep the unsafe edges of the tree. So then we simply have the graph G hat, where we contracted the safe edges here. And then in this graph, we computed 2-edge connected spanning subgraph. And then we use the approximation algorithm by Jane, the 2-approximation. And finally, we output the safe edges together with the solution for this 2-edge connected spanning subgraph problem. Again, an illustration how here, and we can show that this is the 5-approximation. And an illustration of algorithm C is as follows. Again, we have a graph here. We compute a minimum spanning tree. We then contract the safe edges, but we do not keep the unsafe edges. So it might look like this. Then we add the remaining edges of G in this contracted graph. And then we compute the 2-edge connected spanning subgraph in this graph, which might look like this. And then we transform it back to the original instance. You had this contracted edges, and then it might look like this. And here again, you can see we have some cut edges, but these cut edges can only be the edges that we've contracted. And since we only contract safe edges, we always have a feasible solution. Okay, so these are the algorithms A, B, and C. And now we introduce the scaling of the cost of the safe edges. And what do we mean by that? So we define a new weight function, W alpha. And here for the unsafe edges, we just have the same weight. But for the safe edges in F bar, we scale the cost by a factor alpha. And since alpha is between 0 and 1, we actually make this edge cheaper. So it's an incentive to buy the safe edge. And now a minimum spanning tree with respect to the weight W alpha is called an alpha MST. And why is this a good idea to do? Well, okay, consider this example here. And consider algorithm B. Here is minimum spanning tree might look like this. And then in the next step, we solve the tree augmentation problem. And we might buy, for example, these edges. And why did we buy this edge of weight 20 instead of the edge here of weight 10? Well, we solved the tree augmentation problem using a two approximation algorithm, and therefore we cannot expect to buy this edge which is cheaper than that one. And there you can also see why in the worst case we have a three approximation algorithm. Okay, and what happens if we scale the cost? Okay, for example, we scale the cost by a factor alpha equals to 0.8. This means that all the safe edges here, these four edges, they are cheaper now. And you can see, okay, now this edge has weight 8, exactly as this unsafe edge. And we can find this minimum spanning tree like this. And now this minimum spanning tree is much better than the one before, because here you have bought the safe edge. So when using algorithm B, you contract this edge, and then you compute the tree augmentation problem instance. And then a solution to this tree augmentation problem might look like this. So which is, in this case, it's an optimal solution. So you can see it might be actually beneficial to us to make the safe edges cheaper. But of course, you can easily come up with other instances where it's not a good idea to scale the cost. Okay, now consider again this instance, and this is an optimal tree. By an optimal tree, we mean that it's a tree of an optimal solution. And now we do the scaling of the safe edges, not only for one scaling factor, but for lots of different scaling factors. For example, for these 5 scaling factors. And then for different scaling factors, we obtain different spanning trees. And here we can observe lots of interesting observations. For example, if you decrease alpha, since we have a spanning tree which is a special matroid, we will always increase the number of safe edges. As you can see here, the number of safe edges increases when you decrease alpha. And you can also see that there's some kind of threshold behavior for the safe edges. For example, consider this safe edge in this alpha MST. There you can see this edge is contained in this alpha MST, and then it has to be contained in all the alpha MSTs for smaller alpha, because here we only make this edge cheaper. This is also due to the fact that we have matroid properties. And so the threshold value for this edge then is exactly 8 divided by 10, because for alpha equals to 8 divided by 10, this edge is contained in the alpha MST, and for all smaller alphas as well. But for bigger alphas, this is not, the edge is not contained in an alpha MST. And you can do the same for the unsafe edges, but the other way around. Additionally, what we can see here is that we have some kind of charging argument for the cost of the edges that we've computed, but that are not in an optimal tree. For example, consider this edge here. We've bought this edge instead of this edge, which is part of an optimal tree. Well, why did we buy it? We bought it because this edge is cheaper than that one. And we know exactly how much this edge is cheaper than that one. It's precisely 8 divided by 10 times cheaper, because the threshold value for this edge and this edge is precisely 8 divided by 10. That's why you know that this edge here is 8 divided by 10 times cheaper. And you cannot only do this for this one edge, but you can do it for all the edges that are in the alpha MSTs. For example, here also for this edge here, you know that this edge here here we have to take care now, because now we have bought a safe edge instead of an unsafe edge. So we know that this edge here is 3 divided by 2 times more expensive than this one. And we can do this for all the edges here. And we can do it in such a manner that these functions that that go from this edge to that edge, they are actually a bijection. So we do not have, we have a bijection, right? So let me recap what we found out here. We saw that the edges have some kind of threshold behavior. So for an alpha MST with this cost, this edge is contained in an alpha MST, so it will also be contained in all the smaller alpha for smaller alphas. And we can bound the cost of the edges that we have computed.
You have 4 minutes left.
Okay. So just here we can see the threshold values. It's again the definitions. It's precisely what I've said before. And now we have some very nice lemmas. So first, these threshold values, we can compute them in polynomial time. And furthermore, the threshold values are the optimal choice for the scaling factors to be used in the algorithm. So if you have the threshold values and you add some more scaling factors, the algorithm will not be better. So that's an important property. And now we can state the overall algorithm. The overall algorithm
we have lost your voice.
Threshold values, which we can algorithm A, and for each threshold value alpha and W.
I think there is some connection problem.
Now again? Hello?
Now it's okay. Yeah.
Okay. So yeah. Can you hear me?
Yeah.
Okay. Perfect. So where was I? I think I was here at point 4.
Yes.
So for each threshold value alpha from these threshold values, we run algorithm B and C, and with threshold value alpha. What does it mean? By this we mean that we compute the spanning tree using the weights W alpha, and then making it feasible using either the tree augmentation problem or the two-edge connected spanning subgraph problem. Then we use the original weights W. And then finally, we simply return the solution with the lowest cost from algorithm A, B, and C. And now I will shortly show how we obtain the approximation guarantee. So our goal was to obtain the min-max-min problem like this, again, where this FA, FB, FC are simply upper bounds on the solutions computed by algorithm A, B, and C for the threshold values alpha I. And we can simply output the minimum cost of those. Then here, this beta and gamma, they are parameters that depend on an optimal solution. So we have to maximize over those. And they additionally satisfy this condition. And finally, as we have seen that for a given instance, we can compute the optimal scaling factors. So the problem here is that for a given instance, we can compute the optimal scaling factors, but we want to have an approximation guarantee which is valid for all instances. And but here we now have the very nice lemma from before, which stated that if we simply choose some arbitrary scaling factors, we will never be better than our actual algorithm. So for our analysis, we can minimize over these scaling factors. Okay, now the question is, the remaining question is, how do we obtain this function FA, FB, and FC? And unfortunately, we will not have enough time, but just to give an idea how they look like this. Here you have most of the variables here you have already seen, like this alpha, beta, and gamma here. And the remaining 2 variables are actually constants. It's the C2EC and C tab, which is the current best known approximation factor for the two-edge connected spanning subgraph problem and for the tree augmentation problem. So here you can see that actually our whole result is a black box result. So if one obtains a better approximation algorithm for the two-edge connected spanning subgraph problem, then we can bound the cost of, for example, algorithm A in a better way. And then finally, we have to solve this min-max-min problem. And we wanted to solve it computationally because we were not able to solve it analytically. And our idea was, well, we can simply minimize this minimizing. We simply can choose some good scaling factors. And then we are simply left with a max-min problem. And this max-min problem we can rewrite as a quadratic maximization problem. And then finally, the approximation guarantee of our algorithm is bounded by Z, where Z is smaller equals to the functions f a, f b, and f c, and this further constraints. And then finally, simply by putting the constants to 2, which is the current best known approximation factors for these two problems, then we obtain the 2.523 approximation algorithm. And for the bounded weight instances, we have that a 1.5 approximation algorithm for the tree augmentation problem. Then we have a 2.404 approximation algorithm. Okay, yeah, that's it. Thank you. Do you have any questions?
Thank you very much. So please raise your hand if you have a question. There's, okay. Laura Sanita has a question.
Yes, hi. Thank you for the talk. Very nice talk. I have actually two questions, if I may ask. The first one is the following. Two-edge connectivity and tree augmentation, they have actually approximation ratio, which are LP relative for some LP. I was wondering whether this is the same also for your problem, if there is some good LP, which this approximation can be made LP relative.
Yeah, so actually I've prepared some slides for that question. So the very famous ILP formulation for the two-edge connected spanning subgraph problem looks like this. Here you basically have that all cuts, they have to have at least two edges. And this the algorithm from Jane actually works using this ILP formulation. And we can also define a similar ILP formulation for FGC, which basically states that either you have one safe edge in your cut or two edges. And we can show that basically we have the same nice properties for our ILP formulation as in the previous one. But the thing is that because of this 2 here, we have a multiple of 2 in the approximation factor, which then results in a 4 approximation. That's also basically why algorithm A is a 4 approximation. And furthermore, we came up with an integrality gap, and the integrality gap of this ILP2 is 8 divided by 3. Simply consider this instance. The safe edges here, the black ones, they have cost 1, and the unsafe edges have cost 0. An optimal solution has to be like this, of cost 2. But a fractional solution has, with here, the safe edges have fractionality 1 divided by 4. Then you have integrality gap of 8 divided by 3. So it's actually worse than the approximation guarantee of our algorithm.
Okay, I see. Thank you. And just a second question, very quick. What about unit cost?
Yeah, we also considered that version. There we had an even more general result for which we call KFGC, where a subset of K edges may fail, but only from the unsafe edges. And there we also had a general result. Also with a similar style like here, but there we did not need the scaling factors because all this costs are the same. And I think for the normal unweighted FGC, we have a 1.5 approximation using a result by Figen and Schibel.
Okay, okay, thank you very much.
Thanks. Are there any other questions? András Sebő?
The same as Laura's, but then my second question is different. So is there a conjecture? But from your first answer, I understand that there won't be an easy answer because the lower bounds for approximation ratios for these problems are difficult. Often it is the integrality gap that you can bound, and as it became clear from your explanation, your bound is better than the integrality ratio, so you don't base on this integer programming formulation, which gives a worse lower bound. But is there a conjecture? So do you, from all these things, this something come up as a candidate for the exact approximation ratio, or the best that you can do, maybe without a lower bound?
Well, we don't know, to be honest. So we do not have any example where our algorithm is tight. This is due to the fact that we, in our algorithms, we use approximation algorithms, and then we have to find a counterexample for this first approximation algorithm, and this has also to be a counterexample for our approximation algorithm. So we do not even have an example where the bound of our algorithm is tight. Does this kind of answer your question?
Yeah, it does. Okay. But so could it be two with some other, in some other way which doesn't use edge connected spanning subgraph? So do you have any guess, maybe less than a conjecture, for the best approximation ratio?
You mean conjecture for the best approximation ratio for our problem now, or?
Yes, for your problem now, yes.
I think it's closer to 2, but I have no idea how close. Yeah, to be honest.
Okay.
Thank you. So, yeah, I'll unmute everyone and thank the speaker.
How much?